So this is the second deliverable on the Jeffcott rotor, showing the governing equations and a brief little model of the system. Looking here up at the top up here, that's the model of the system, starting with a mass M in the middle, two stationary bearings on either side. The distance between the two bearings is the length L, and the stiffness of the shaft will then be written by K equals 48 EI divided by L cubed. Then the governing equations, it might be easy to pause it and then you can see this. But the governing equations would then, there would be one for the X and one for the Y, since there's two different systems, two different directions. In the equation, U is just a position vector. And so there's term 1, term 2, term 3. Term 1 would be the mass times the second derivative of the position vector. Term 2 would be the damping effects times the first derivative, while term 3 would include the stiffness of the shaft, just times the position vector itself. And then on the other side, that's where the external forces are taken into account, and E represents the vector of the displacement from the center mass. Omega in this case would be the rotating speed, and this would be multiplied by cosine omega t for the X. For the Y, it's the same thing, but you would include sine omega t, and it would be taken into account for the Y direction. Then we can also look at an undamped and damped. For an undamped system, which would exclude damping, and there would be no displacement from the center mass. Once again, one for the X, one for the Y. Right here and here, equations 2 and 3, or 3 and 4 rather. The B terms, those are just constants, and it would be multiplied by cosine omega t, and then added to the other constant times sine omega t. And then the Y would be the same, including cosine for the second term. Then for a damped system, which would exclude the displacement from the center mass, we would have equations 5 and 6 at the bottom, one for the X, one for the Y. The constant terms times cosine omega t plus the other constants times sine omega t. And then all of this is taken and multiplied by E to the damping ratio times omega n t. And then looking up here at the top, just a reference for the variables used. So the damping ratio is equal to C over the critical damping factor, which is 2 multiplied by the square root of K. And then the natural frequency is equal to K over M.